final talk of the conference. We've got Mahan, who's going to tell us about cubulating drill circuit bundles over.
Okay, thanks, Henry. Thank you very much. And thanks to the organizers. And since this is the last talk, and I suppose this is some kind of custom of having senior citizens at the end. So thanks very much to the organizers, Genevieve, Dani, who is in cyberspace, for this fantastic conference. I've learned a lot. I'm sure every one of us has. And there's another bunch of, very pleasant things to announce. I suppose, should I do it? Would you like to do it? All right. So let's see. So this is all joint work with my student, Biswajit Nag. So where does this all start? Okay. So it starts with this question. E and G stand for that guy. And so here's the question. Let's see. G is hyperbolic. And if you find it indecipherable, just stop me. I have difficulty reading my handwriting at times. Okay, G is hyperbolic. G has a hierarchy. Is G cubulable? Okay. I think this appears in Dani's ISIM talk somewhere. Note that there's no adjective before hierarchy. Okay. So, and as far as I know, there is no known counterexample either. Okay. All right. So, what are kind of So this is so of course theorem the quasi-convex. So there's of course the quasi-convex hierarchy. I was grinning to myself when Lars was writing hierarchy, and I seem to be having the same problems. Okay. Quasi-convex hierarchy theorem. This is Dani's. And there's one other class of examples. So free by cyclic, Mark Hagen and Dani. And so there's a very specific form of this question that I wanted to look at. So specific question, specific case of this above question is, let's see. So I'll, yeah.
When you say hierarchy, you mean
terminating in the trivial group, let's say. It's ambiguously stated on purpose. Interpret it any way you like to get a theorem. That's, I think. Yeah. No, it has to go all the way down to something manageable. Yeah. So I'll be being Cavalia about writing fundamental groups. So these guys, Mi, these are three manifolds fibering over the circle with fiber F. Okay. So this is fundamental group. Take 2, 3. What does this look like? It's basically you have this is your graph G, and you have a fiber. Okay, so you have a fiber bundle over a graph, and so this can be decomposed as the amalgamated free product of two of these three manifold groups over now a fiber subgroup. Yeah, and question, the question is G cubulable? So phrased in this silly form, the answer is no in general. What you can do is just take no in general. For example, M1 is equal to M2. So basically, oh, these are hyperbolic. Mi hyperbolic. Three manifolds fibering over the circle. And so basically, yeah, so you have this three manifold fibering here, three manifold fibering here. You have the fiber surface sitting over this point, and you just take an F cross I and you glue these two things together. And what you're asking is whether this guy is cubulable or not. So this certainly has a hierarchy, right? Well, yeah, you can cut along the fiber, and then you get 2 3 manifolds. Those don't quite have a hierarchy, but well, they do. I mean, they are Haken. You can still cut further. And anyway, I mean, I think here the point is that after you do the first cut along the fiber, you have two guys which are cubulable by Egal's theorem. Okay. So what's the problem with this? And in this form, you really need to assume that G is hyperbolic. So if you just double, then you don't get something that is hyperbolic. The fiber is exponentially distorted. So yeah, I mean, why is this? I won't write this down. I'll just say it. Because the fiber is distorted, the isoparometric function is exponential. Yeah, so it's distorted exponentially in both directions. So you take, say, some line, some geodesic in the fiber, which is exponentially distorted. So those are going to bound. I mean, so there's something like this, and this is supposed to be linear. This is something like e power n. This is n. This is n. And so you can't cubulate these because it does not. I mean, they don't satisfy a quadratic isoparometric inequality. Okay, so certainly G hyperbolic is necessary in this assumption. So G hyperbolic. What does that mean? So you have 1 going to phi 1f, G going to free group going to 1. So this is the closed surface. G is hyperbolic, and there's various, I mean, so it connects up with, so this means that this F2, this is, and this, I think this terminology has come up here before. It's a convex co-compact subgroup of the mapping class group of F. Okay. So this is, yeah, alluding to Hammenstadt and Kenton line. Yeah. So these are the guys that we wanted to, we started off wanting to cubulate, and met with very, very minimal success. So theorem, and this is where the story starts. So this is going to work with Jason Manning and Mika Sagiv. I won't say what the precise form is. I'll just say there exist examples of M1 star F M2 that are cubulable. I think this word cubulability has various meanings. So for me, it will just mean that there is a CAD0 cube complex on which the fundamental group acts properly, I mean, acts geometrically, properly co-compactly. Okay, so there are these examples. And it was a lot of effort, and finally we got very little out of it. I mean, we just got some, yeah, just a few examples. Okay, and so Henry suggested that after the recent incendiary developments in the other house, I should come up with something. So I was reminiscing about, I mean, I was watching this film, which I think all of us have probably seen, Dr. Strangelove, yesterday. Yeah. And so I think there's a subtext which to this title. how I learned to stop worrying and start drilling. Okay. So let's see. So what are, and this is actually a nod to Bruno's comment. I mean, that's hyperbolic manifolds. After you drill them, they become much easier to handle. So drill the bundles. So I won't give the most general form here, but should illustrate at least one case where you can drill and hope for something, some cubulability results. So what's a drilled bundle? Drilled bundle. Okay. So again, so E is equal to now so you have E fibers over a graph, fiber F, phi 1 E hyperbolic. This is going to be my setup throughout. And so F naught is a fiber, and sigma contained in F naught is a simple closed curve, and they're, I mean, essential. In case I forget, all my simple closed curves will be essential. And then drill out a small neighborhood of sigma in E. Essential simple closed curve allow sigma to be a multi-curve, allow sigma to be a multi-curve, simple of course, and allow finitely many fibers not. Okay. So essentially, so what are we doing here? So let's take a 3-manifold as an example of a bundle over a graph. So you have stuff here, fibers over an interval, and so you pick some bunch of fibers, and you maybe fill out this guy here, some other guy, and a third one. All that you really need to ensure is that fibers which are side by side, I mean, there's none of these can be homotoped to the next they represent distinct homotopy classes, let's say, in the whole 3-manifold. Okay, then just remove these guys. So that's what we are doing. Pick some finitely many fibers, finitely many simple closed curves, remove them, and that's what we call a drilled bundle.
Take 3 images of regular points so that there's a little neighborhood.
That's correct. Yeah. Regular point for F, for G. That's correct. Thank you. Yeah. Okay. So now I think I'm about to say what's the upshot of all this is. So theorem. I'll use a sufficiently, and I'll say what this is. Drilled bundles are cubulable. So what's sufficient? So what does that mean basically? See, the thing is, what we are trying to say here is that the obstruction to saying that all these guys are cubulable is the obstruction to bundles without drilling being cubulable. Okay, so what does that mean here? So more formally, definition, E belonging to G is drilled. Yeah, so I think this is really an answer to Dave's question. So my edges will be denoted by E, and I'll mean interiors of edges. Yeah, and if I want the closure, I'll say E bar. Okay, so E is drilled if there exists little x belonging to E such that f sub x, the fiber over x, is drilled. And sufficiently, what is that? Sufficiently drilled. What does that mean? So define G prime to be G minus union of these edges E, where E is drilled. Is up. Is up. Okay, and so each component of G prime gives a cubulable bundle. That's what I mean. So that's what sufficiently drilled means. So for instance, what's the simplest example? I think I've gotten the thing here. Yeah. So you have this example, M1 star M2, and I'll actually really think of just this one example from here to the end of the talk. So you have a three-manifold fibering on the one side, three-manifold fibering over the other side. You don't drill those guys, but take some fiber sitting over this, the bridge of the eyeglass, yeah, and drill it. Okay, so that's an example of a. So let me just say what this thing is here.
Assuming that your undrilled bundle to start with is hyperbolic.
Yeah. That's that. Yeah. So these are standing assumptions, and I start off with something that is hyperbolic. So this is its purpose. So example of sufficiently drilled is, let's call this E. E, that's a sufficient drilling. Why? Because the two sides, now they are three manifolds fibering over the circle, they are cubulable. Okay. All right. So now, yeah. So this is basically the content of what I'm going to be talking about. And at this stage, I think it's trying to get back to the motivation before I mean, okay, so let's now back to three manifolds. Is there a clock somewhere here? Oh. Oh, wow. Okay, good. That's not so bad. Okay. So back to three manifolds. So yeah, so I guess this is, yeah, in some sense, this is a quantum superposition talk. The motivation comes from three manifolds. It ends up giving something about cubulations, but the strategy is through subgroups. Okay. So back to three manifolds. So let's cubulate. So okay, cubulate drilled three manifolds fibering over the circle. Okay, I was thinking of using recubulate, but that word's already been taken. So let's go back and look at the strategy for cubulating three manifolds. And so in this setup, in the setup of bundles over graphs, you do not have, I mean, so what's the usual? I mean, the strategy is drilled or, well, I mean, an undrilled three manifold is also a drilled guy, where the drilling locus is empty. Okay, so the strategy is, so you start off with enough surface subgroups, and these are quasi-convex. This is due to Kahn and Markovich. Then you use Bergeron-wise to cubulate, and finally apply Egal's theorem, conclude That's how one goes about cubulating, even in the case of the general case of three manifolds fibering over the circle, particular, say, first bit number 1. That's something you have to do. Pardon me? This is, yeah, so this is the case where drill locus is empty. Okay? Yeah. So the undrilled examples, yeah, undrilled guys are examples. Okay. But in this setup, there's no Mahan Mj to help you out. That's actually just one of the problems. The other problem, and essentially this is, well, no Mahan Mj. What does that mean? So, okay, so there's no Mahan Mj theorem so far, and yeah, I mean it has no homogeneity. I mean you can't hope that, I mean, to push anything like ergodicity or frame flows or stuff like that through. And
All right. Are we in three manifolds?
we are still in. Oh, yeah. In bundles of graphs. So there's no Mahan Mj, but that's just one of the problems. The boundary of G is, I don't know a better word for it. It's a right royal mess. Okay. You want me to give a more precise version of this? So the boundary is it's not a sphere. I mean, essentially, it's a quotient of a sphere in some horrible way. Okay. Yes, Daniel.
I was just thinking the boundary is a collection of torals, but I understand.
Oh, the boundary of G. Yeah, I think you did not read my letter correctly. Okay, so yeah, so the boundary of G is a mess. Okay, so it's you can't quite use hyperplanes. So what do we do? So it's back to the drawing board. However, I mean, and so the only so the strategy that's left is, well, the strategy is use the quasi-convex hierarchy theorem, which means hunt for a quasi-convex first cut. Okay? So if you have a Harkin three manifold, so this is really, in some sense, doing three manifolds all over again. And so Thurston's combination theorem was, well, I mean, if you have, I mean, so this is part of something that really goes back to Thurston. So if the first cut for a three manifold, any closed three manifold, is quasi-convex, then you have a hierarchy which is quasi-convex. Yeah? So this is theorem. Yeah, so I'm going between three manifolds and graphs. So
like, is your group hyperbolic or is it relative?
at this stage, it's hyperbolic. So if M closed hyperbolic has an embedded quasi-convex surface, it has a QC hierarchy. All right. Yeah. So now here's the thing. So this was actually this stuff really goes through for bundles. So for G, and now okay, I'll just write undrilled. No, this is not good. E, right? E is an undrilled bundle. E admits a quasi-convex crack. I'll say what this is. Then if E admits a QC track, then E admits a quasi-convex hierarchy. What's a track? So essentially, okay, so now this is 2-3 manifold. So a track is the generalization of an embedded surface, but now in this pre-complex. Okay, so it's essentially locally it looks like, I mean, it's a 2 complex such that the 3 complex locally looks like that cross I, and it separates and so on. Yeah. Can you call it a branch surface? So the thing is that would be a little misleading, because branch surface means you want something like a 0 angle. That's not important here.
Call it a two-sided 2 complex.
It's a 2-sided 2 complex, but there's a little more. It's locally separating. That's all fine. But you want something more. You want it to be pi1 incompressible. Yeah, but the rest is exactly that. Okay. I won't get into further details about tracks because that's not going to be relevant. I say this because the strife in this theorem is to find such a track. Okay. So essentially, it's basically yes. QC means quasi-convex. Quasi-convex. So you have this subcomplex, right? You lift it to the universal cover. That gives rise to a quasi-convex subgroup. Okay? It's incompressible. Oh, a quasi-convex hierarchy. Oh, it means basically that after you've decomposed along the, so once you have this quasi-convex track, the group splits along its fundamental group. So now you have the new vertex group that you have, or new vertex groups that you have, and those can be further cut along quasi-convex subgroups of those, all the way down to the trivial group. Okay, so the problem there was essentially finding this track. Yeah, so essentially it's like hunting for, and it's in hindsight, it looks natural. I mean, it's very few 3 manifolds admit a quasi-convex embedded surface, right? So, I mean, Karl Markovich gives guys which are immersed, but things which have embedded, those are rare, yeah, and in a fairly precise sense. So at this stage, decided to drill. Okay. All right. Okay. So now, still in 3 manifolds, but let's prove or observe a baby version of, I think this particular part is probably due to Danny, because it's a, so drill 3 manifold fibering over the circle. Okay. And it's again, so you have 0, 1, you have surface, and now you really don't need to bother which fiber you drill, just drill some. Yeah. So let's say X, and you have F sub X here, you have a curve here, and you drill it out. Okay. So you have a, so for the purposes of this talk and this talk only, this is something I'll refer to as a drilled 3 manifold fibering over S1. Okay, but there's a gluing map here. All right. So how to cubulate? Yeah. So once you've drilled, you get a relatively quasi-convex surface. It's basically for free. Well, not free, but there's a theorem behind it, but there's something here. So essentially, once you've drilled, you've removed this curve. Yeah. So the 2 parts of the surface, and it could be non-separating, it's one surface. So let's say that's F1 minus sigma. This guy is relatively quasi-convex in pi1 M drilled. Okay. And this is a special case of a, I mean, this is a theorem which this is relatively quasi-convex. Well, not quite this, but Okay, so let's see. So why should you believe that this is relatively quasi-convex? And basic reason. And there are more sophisticated reasons, but we are trying to sort of do this stuff with at least 1.5 hands tied behind our back. So the reason is that F1, each component of F1 minus sigma is quasi-convex in M. And just to emphasize, I'll write M undrilled. So even before drilling, you take one of these subsurfaces, and that's quasi-convex in the whole thing. And this is an old theorem. Let's see. This is due to Scott and Swaroop. Maybe 91, maybe 90, thereabout. Okay. There's a question. So there's something I did forget about things. Let me see. There's a question about existence of QC tracks, but I've moved on. So maybe I'll return to it at the end. Okay. So this is the real reason. So it turns out that this guy F1 minus sigma is relatively quasi-convex. So what do you have now? F1 minus sigma. I am being familiar with the surface and the group it carries. So F1 minus sigma is rel QC so this is, each component is quasi-convex in the undrilled guy. So after drilling, you get something that is relatively quasi-convex in M drilled. Okay. So there's something to be proven here. There is something to be proven here, and it turns out to be, something one has to do work a fair bit more in the graph case. But let's go on with this and see this through to the end. And now there is a version of so this is 15.1 from the book. From the book of the wise. All right. Okay. So what does this say? What does this theorem say? So let's see. So G is equal to pi1, a graph of groups. G is relatively hyperbolic. G is hyperbolic relative to abelian subgroups. And then you have a whole bunch of assumptions. Each GV vertex group is special or virtually special. Maybe it's better to write virtually special here. Each GE is relatively quasi-convex, and let's see. For all, so G, this is going to be terrible. So G minus E, pi1 G minus E, any abelian, any, let's say Z2 so you remove this edge and you look at any Z2 in the graph of groups corresponding to throwing away the edge. This intersects GE trivially. I think I've gotten all my hypotheses. Wait. Let me just see. There's one relatively hyperbolic, edge groups relatively quasi-convex, and this. I think that's fine. Vertex group special. Okay. All the things. Then pi1 G is virtually special. So essentially, if the collection of Z2 is empty. Yeah, this is the quasi-convex hierarchy theorem of Y's. Okay, so so this now let's look at this. This is the hammer with which we hit this grilled free manifold and find an extremely inefficient way of proving that these guys are cubulable. But then, see what's happening here is that then what's the vertex group here? So let's go back to this example. We go back there. So you have your surface here. You've this is stuff you leave in, right? I mean, these are, and essentially you remove the interior of this guy and then you glue. Yeah? So this is your torus here. So M minus the interior of this torus here. Yeah. So this gives you the pi1 of this. This is equal to so there's a vertex group which is pi1 of the fiber. There are, well, if it's separating, there are two edge groups. And now you have a pi1 of surface cut 1. And there's another one which is pi1 cut 2. So there are these, so this is your, this part, this is f cut 1, f cut 2. I mean, there are two bonding maps into the surface. This guy is special. Yeah.
Surface minus the angle left, the surface minus the angle
I am gluing, no, this is the T interior. I'm removing only the interior of this solid torus. So I'm gluing this whole surface to this whole surface. Yeah. Exactly. Yeah. Yeah. So this is special. This is rel QC. This is rel QC. And if you remove this, there's a single edge here, right? I mean, well, there are two edges, but if you remove any of these edges, yeah, there's an E1 here, there's an E2 here. So this is E1, this is E2, this is E1. If you remove that, then you remove the torus, and there are no tori to bother about. So the hypotheses are satisfied. So this guy, this grilled free manifold is special. Okay? So it looks like, yes? Oh, it's virtually special. Yeah, by special, I always mean virtually special. I always mean virtually. Sure. Yeah. Okay. So that seems to be I mean, it's one you do have a whole bunch of things available, and then you go back and revisit and find a really painful thing that gives you much less. Okay. But then let's see. So this is a strategy that you can apply. Can apply this strategy to grilled bundles over graphs now, where the graph now need not be a circle. Okay, that's what one gains through this process. Okay, how? So what did we really assume here? At this stage, I think I'm done with free manifold for the time being. And so return to grilled bundles over graphs. Okay, right? So let's see. So you have f sub x, suppose this is grilled. Okay, so there's a fiber which is grilled. Then, so suppose two hypotheses. One, that E grilled, so you've drilled some bunch of these guys out, is hyperbolic relative to some bunch of Z plus Z's. I mean, each time you drill, you're going to get a torus, and you have this finite collection of boundary tori. Now, boundary in the real boundary sense. Yeah.
Is the
E is the total space. E drilled is E minus, because that's no longer a fiber bundle, right? So suppose you have this, and 2, I'll call that, let's see. So F cut, let's say, basically it means after you've removed that guy, this is relatively quasi-convex. Then can apply theorem of Wise to the resulting graph of groups. So this is, so note that the new graph of groups that you get, it's now got edge groups which correspond to the cut surface, right? So essentially now those are relatively quasi-convex, so you can cut along those, which means essentially a drilled edge can be removed from the picture. So so now go back to the original statement, if you remember. Basically, it was something about sufficiently drilled. Yeah. So you remove all the edges that you've drilled. Yeah? You have your graph, original graph now falls into a bunch of components. If that guy is cubulable special, then the theorem will give you that the whole thing is special. All right. Ah, fantastic. Okay. I have, yeah. Where? 2 is? 2 is not satisfied? Ah, I was going to say it's always satisfied. Yeah. So that's, yeah. So the thing is, so suppose you had this, yeah. Suppose you had this, yeah, and you want to, yeah. So why should you believe? So now first, I mean, before, I don't know whether I'll be able to get to the actual proof. So basically, what does it boil down to? It boils down to, I mean, the theorem really boils down to proving relative hyperbolicity of the drilled guy, 1, and relative quasi-convexity of the cut surfaces. Yeah. Okay. Yeah. And here we can actually leave the cubulable world and just look at drilled hyperbolic bundles and cut surfaces. Yeah. So this is no longer, I mean, there's this part, I mean, the cubulability theorem is something that's relative to the vertex groups of G minus E, but the theorem, if E is hyperbolic, then E drill is hyperbolic relative to V plus Z's, and F this, and each F cut is rel QC. Okay, so that's what this whole thing boils down to, and that's what we need to prove. Okay, so why should you believe this? And there is an analog of, so there is an analog of the Scott-Swarup theorem for 1 goes to phi 1f, goes to G, goes to Fn, goes to 1. This is due to Spencer Doerr, Autumn Kent, and Chris Leininger. So yeah, there's a different take on that by Casarafi and me, but this is really the theorem, which basically says, well, before drilling, I mean, so there is an analog of the Scott-Swarup theorem, which basically says that, look, which basically implies that if you take one of these fiber surfaces, take a subsurface, it's still quasi-convex, and this is, so phi 1f cut is QC in G. This is now hyperbolic. Yeah. So, okay. So yeah. So this gives you some hope. Yeah. Yes. Then you're going to get Z plus Z's, right? So there's going to be some parallel. I mean, there's a, yeah. It's.
You already said don't do that.
Yeah. Oh. That's part of the when the definition of drilling excludes that case. Yeah. Homotopically distinct cast. Yeah. Okay. Yeah. Sure. Yeah. All right. So this guy is quasi-convex in G. So this is giving you some hope. I mean, as in the three-manifold case, so should be able to push this through to relative hyperbolicity. Okay. So now there's a. So now I'll give you again. So drilling. Yeah. So there are. I don't know whether I'll. Yeah. I think I have less than 5 minutes left, probably. 6 minutes. 6 minutes. Yeah. So the thing is, yeah, I don't think I'll probably say a word about how we actually prove this, but before that, I'll just maybe one sentence to that effect. But why should you believe this? So let's see. So there are relatively hyperbolic theorems. Yeah. So these are things that theorems. So these are things that exist in the literature. Unfortunately, none of it is something that we could take off the shelf. So I think the first version of this is by Alcock, Belegradic, and the version which is most relevant to this, but not quite applicable, is due to Belegradic and Rushka. So essentially, what is it? So take again, go back to a hyperbolic manifold, take a closed geodesic, three-manifold, closed geodesic, yeah, simple closed geodesic, do a branch cover over it, yeah. So what happens is that the curvature concentrated at that vertex increases, right? Go on doing this, yeah. In the end, what are you going to get? So pass to limits of branched covers over simple closed geodesic. And what are you going to get? You get drilled M. So basically, you take, so this is, so you started off with your three-manifold, you took a geodesic, and you remove the geodesic. What's the metric on it? Topologically, you get a drilled manifold. And the metric, well, more precisely, the pseudo metric on this is, let's say, drill along sigma. So it's M minus sigma with boundary of n epsilon sigma partially electrified. What does that mean? So this is, what is this? This is something like circle cross a circle, and say this circle corresponds to the sigma. This circle is given the zero metric. Okay, so that's what you get in the limit. So essentially, you've removed this. You've got a torus, and you've got the meridian, and you electrify the meridian. Yeah? So that's the limiting metric that you get, and it's a limit of these hyperbolic guys. So you have an infinite amount of negative curvature concentrated there, and from here, in this very special case, for this particular case, yeah, this is a. I'm being very unjust to the actual labor that went into this, but this is roughly the idea. Okay, but the key point here is this partially electrified thing. So we don't have local control over the metric here, right? So, well, I mean, so you can't quite do this. Right? There's another bunch of so group theoretic. And this one is actually a little bit of pressure on the authors to finish writing their business. Group theoretic drilling. Yeah. Let's see. Groves, Manning, Poseida, let's see, Hysinski, let's see, Sisto, Walsh. Yeah. And I think, I've, yeah, all right. H, yeah. Yeah. All right. So since most of the authors are here, this is guys better. Yeah. Yeah. I mean, I was actually, I looked at it and then I asked Jason, look, have you guys done this? Can we take this off the shelf? No. Okay. And then I asked Daniel for some other bit about what they were doing when I met him. And well, so you can't take this off the shelf either. So back to the drawing board again. Yeah. And I have 1 minute left. So low tech. I mean, I have a suspicion that I'm rediscovering the wheel here, and I'm sure there's somebody who will be able to come up with it. So this is a very low tech solution. Low tech solution is guess geodesics. Okay. And this is essentially okay. So what do you want to prove? You want to prove that this partially electrified guy, yeah, there's the torus. So you have to pass to a universal cover. Yeah. So guess geodesics first in the, so prove first. So guess geodesics. So first step, this is the guessing geodesics thing that goes back to Mason-Minsky, Hammenstadt, Bowditch, and this part is prove hyperbolicity, genuine hyperbolicity of the partially electrified M drill, and then the universal cover. Okay. So the first step is to use guessing geodesics from there to prove hyperbolicity of this guy. So we can't quite use the local curvature. So you prove that. And then, and this is really the last step, another beautiful unpublished paper. Have I mentioned that? There was S was there, right? Yeah, okay, good. So this is guess geodesics in relatively hyperbolic. So essentially you take the geodesics that you get from guessing in the first stage, you assume you've proven hyperbolicity there, then you translate all that, but now the relatively hyperbolic, I mean, things that are hyperbolic relative to are pretty controlled, they're flats, yeah? So you have entry points, exit points, and you have more or less well-defined relatively hyperbolic objects, relative geodesics coming out of that, and you prove that again. Okay, so thank you. Yes, Sam.
How should one think of triple F M1 and M2 where the amalgam of M1 and M2 over F is hyperbolic, say in terms of the representation of the common fiber subgroup in BSL2C cross BSL2C?
Ooh. No, I'd love to know that. I mean, I don't know. So Sammy is asking, how would you think of this fundamental group pi1m? So pi1e, the undrilled object, yeah? Can you think of it as something sitting inside PSL2C cross PSL2C? No idea. You just know that it's linear because it's special. Sitting inside PSL2C cross. See, the problem is that the fiber is hopelessly distorted, right?
I'm just wondering, I mean, so you're saying that the double does not work.
Yeah, the double does not work, yeah.
How should these fiber sub, like how should the two representations of the fiber subgroups in PSL2C be different?
Oh, that's the hyperbolicity criterion. So basically, I mean, there are, yeah, it's the whole group is hyperbolic. That's what saves you in this case. I mean, from this particular problem, yeah. Some hack. I don't know. I mean, so here's something that's, yeah, I mean, essentially, is there even a rank 1 group in which this guy sits? I don't know. Yeah. I mean, you're asking about PSL2C cross PSL2C. Okay, that's not rank 1, but.
I mean, I'm not, sorry, I'm not asking about a representation of the whole group. I'm just talking about the F.
About the F?
I mean, F sits inside PSL2C in one way.
Yes.
Via M1, another way via M2.
Yes.
How are these
representations connected? Oh, okay, that's, yeah. So that's relatively let me just know. Let's talk about it later because, yeah, I mean, I don't want to say something which and then said many wrong things before. So that, yeah, I'll have to think about it. But I think that there's something there and something you can say about it. I mean, essentially, see, representations which correspond to fibers correspond to these, basically these double limit theorem of Thurston gives you these representations. What this basically says is that, well, the laminations are distinct, right? And then there's some condition on the translation length, maybe.
If not, let's time.